How's it going, everyone? So today we're going to be covering elemental composition of pure substances and right after empirical and molecular formulas. To start off, we need to talk about three distinct units in which we refer to as compounds in chemistry. We have atoms is one way to refer to them, molecules, and then we have formula units. Atoms, we know, are those structures that have a nucleus in the center with some number of protons, some number of neutrons, and then electrons in some arrangement outside of that nucleus. Molecules, then, take a certain form, a very specific form, and they have discrete differentiable units. If I were to talk about water, H2O, water always looks as such, and this is always going to be one molecule of water. Molecules tend to be formed from the periodic table by taking elements only from the right-hand side. So I bond a bunch of elements from the right-hand side. We haven't defined that term bond yet. That'll be later on. And it so happens that that tends to make molecules. It pretty much always will make a molecule by definition. Then formula units are things like NaCl, sodium chloride, so table salt. If you look at the periodic table now, you're going to have one element from the left and one element from the right that makes a type of salt. And these are all going to be differentiated by formula units. If I had a sample of salt, what you're going to see is sodium, chlorine, sodium, chlorine, sodium, chlorine. And this ratio of the two elements existing within my sample. The smallest ratio you have will be one sodium and one chlorate. So we refer to it as sodium chloride with one for each. If you tried to make sodium 2, chlorine 2, it doesn't make any sense. That's because there's no distinct unit of sodium chloride in this sample. In water, we have H2O. And if you had a sample of water, it would just be a bunch of this structure that we just drew over and over again. But here, that's not the case. This is all jumbled up next to each other. And if I were to take any segment of salt and split it up and look at it, all you're going to see is a bunch of these units over and over again. That distinction is one primary way of looking at the differences between molecules and formula units. That being said, there is a parallel for ratios present in molecules. When we're talking about molecules, there's two ways to refer to their formulas. And by formulas, I mean something like H2O, so it's chemical formula. We have empirical formulas, and we also have molecular formulas. Empirical formulas only exist to give you that ratio. So let's say I have a sample of some substance that has carbon and hydrogen. All I know about my substance is that for every one carbon, it's going to have two hydrogens. So you might denote it as CnH2n, where N is going to be that same value between them. So if I had 4 carbons, I'll have 8 hydrogens. And this doesn't mean in total. This just means one specific molecule for one molecule. So if I had a sample of this CnH2n, whatever the exact values end up being, you'll see that unit over and over and over and over again. Molecular formulas, on the other hand, define these values. So now instead of N's, we'll have perhaps C5H10. And this tells you that every single molecule of C5, every sample of C5H10 is going to exist in this exact same ratio. So you had water H2O, well here in this case you'll have C5H10. So it'll be 5 carbons and then 10 hydrogens around it. Not exactly sure how they're bonded, but that's more or less what it'll look like. On the topic of empirical and molecular formulas, we have to be able to know how to derive a molecular formula given information to find an empirical formula. So one typical question would be saying, I have a sample of an unknown compound. All I know is that by mass, my compound is going to be 40% carbon, 6.7% hydrogen, and then 53.3% oxygen. Given that 1 mole of my compound weighs 180 grams per mole, what is its molecular formula? So when it comes to finding out, the first thing we have to do is you assume a 100-gram sample. What that means is, okay, they told us my values for percentages as far as weights go. If I say I have 100 grams of this stuff, I can literally just turn those percentages into grams, and I have actual values to work with. So we'll start off with 40 grams of carbon in this substance, 6.7 grams of hydrogen, and 53.3 grams of oxygen. And obviously this will add up to 100%, 100 grams in this case. We need to find out what 1 mole of each of these weighs. If we divide it by that value, now you get the number of moles of each of them. And every time we're doing any sort of chemical analysis, the mole is going to be a very, very important unit. That's what lets you generate that apples to apples comparison between things. For carbon, its molar mass is going to be 12.01 grams per mole. For hydrogen, it will be 1.01 grams per mole. And for oxygen, it will be 16.00 grams per mole. So we end up with 3.33 moles of carbon. We have 6.63, and these are all estimates, by the way, moles of hydrogen, and again 3.33 moles of oxygen. What do we do with these values? Well, as it turns out, if we take them and divide them by one constant value, we now have a ratio between them. And we have a ratio here, but we can't read decimal values. You can't put decimal values into a molecular formula. So I'm going to go ahead and divide everyone by 3.33. Why did I choose this number? Because it's the smallest number here. The right answer is to always choose the smallest number present. And obviously 3.33 is present for 2 of them. After that, you end up with a value of 1. Here, this is roughly 2. And if you do the math, it's 1.99 something. You're definitely allowed to round that up to 2. And this is going to be 1. These values are literally the subscripts for writing out that n equation. So there's a 1 right here, there's a 2 here, and there's a 1 right there. Now, what will the last step be? At this point, we've solved for the empirical formula. Now it's time to find out the molecular formula. Remember, they told us we have 180 grams per mole. Right now, if I was to define C1H2O1, what would this weigh in grams per mole? Well, I know 1 carbon weighs 12.01 grams per mole, plus 2 hydrogens, so 2 times 1.01 grams per mole, and then plus 16 grams per mole. We end up with approximately, well, from this it's going to be 30.03. So for simplicity's sake, we're going to round that up to 30 grams per mole. Okay, what do we do with this value? Well, we also know that there's 180 grams per mole in 1 mole of my substance. If we take 180 grams, and divide that by 30, we end up with 6. Well, 6 is the value for N. So now we can go back to this formula, the empirical formula that we derived, plug in my 6 value, and it ends up with C6H12 and O6. Then this is going to be your actual molecular formula. At this point in time, there's only one issue that you could potentially run into. Say we're going to make a distinction coming out from here, right? And we had some substance, they gave us all these values, and we wound up with 2.5 moles of element X, and then 3.75 moles of element Y. If we divide each of these by the smallest number, 2.5, you're not going to get an exact value this time. Here you'll get 1, and here you'll get 1.5. But we can't use 1.5 in any empirical molecular formulas. So what do? We're allowed to multiply all of these by 2. And there will always be some value you can multiply them for them all to end up being whole numbers. If there isn't, that means you messed up somewhere on the way. This ends up being a 2, and this ends up being a 3. So now my empirical formula in this case would be X 2N and Y 3N. That's all for today, guys. Thank you very much, and see you next time. Don't forget to subscribe and hit the like button. Take care.